Quantum atom theory, a phase-based unified conceptual framework for time, gravity, and causality. This work preserves standard equations but reinterprets their physical meaning. Independent researcher Nick Harvey, introduction. Modern physics successfully describes nature using quantum mechanics and general relativity, yet the conceptual foundations of time, gravity, and inertia remain unresolved. Gravity resists quantization. Time lacks a microscopic definition, and inertia is often postulated rather than derived. Quantum atom theory, QAT, addresses these gaps by reinterpreting known physics through a unifying geometrical and dynamical process rooted in phase evolution. QAT does not reject standard equations. Instead, it reinterprets their physical meaning. The theory is grounded in the idea that phase exchange is the fundamental physical event, and that macroscopic laws emerge statistically from this microscopic process. Emergence of time from interaction. In quantum atom theory, time is not a background parameter, but an emergent quantity arising from irreversible phase exchange. Every photon-electron interaction introduces a finite delay associated with absorption and re-emission. This delay accumulates, producing a local arrow of time. Between every cause and effect lies a photon-electron coupling. Each interaction forms a tiny sphere of possibility, geometrically represented as a block sphere. A point on its surface corresponds to a coherent quantum state defined by phase and probability. Photon polarization and electron spin share this same spherical geometry, indicating that light and matter are two expressions of one process. As interactions proceed, coherence is gradually lost to the environment. The block vector shrinks inward, representing increasing entropy. Time advances as quantum possibilities collapse into classical facts. Principle and spherical geometry. Huygens' principle states that every point on a wavefront acts as a source of secondary spherical waves. Quantum atom theory adopts this principle as fundamental. Spherical wave geometry is the natural consequence of phase propagation in an isotropic universe. Spherical wavefronts define equal phase surfaces. The inverse square law emerges directly from geometry as interaction density spreads over a surface area proportional to 4 pi r squared. This same geometry underlies electromagnetic radiation, quantum probability distributions, and gravitational behavior. Phase delay fields and gravity. In quantum atom theory, a massive object is not a source of force, but a phase delay field. The internal complexity of matter, sustained photon-electron interactions, slows phase propagation locally. This creates concentric spherical phase surfaces with increasing delay toward the center. Motion follows phase gradients. Objects accelerate toward regions of greater phase delay, producing what we observe as gravitational attraction. Gravity is therefore a secondary, collective phenomenon, not a fundamental interaction. Because phase gradients are spherically distributed, gravitational acceleration naturally obeys the inverse square law. Freefall, weightlessness, and the equivalence principle. In quantum atom theory, objects in freefall do not experience gravity because no new phase gradients act across them. Gravity is not a force pulling on objects. It is a phase gradient defined relative to the surrounding environment. When an object is freely falling, all parts of that object share the same causal history and the same phase delay structure. There is no internal phase difference for gravity to act upon. Because gravity arises only from relative phase delay, a freely falling system is locally phase neutral. This is why a spherical firework falling through the sky remains perfectly spherical, and why astronauts in orbit feel weightless. Weight is not caused by gravity itself. Weight appears only when external interactions, such as contact with the ground, impose new phase gradients across an object. Freefall is therefore not the absence of gravity, but the absence of external causal interruption. This directly explains Galileo's observation and Einstein's equivalence principle within a causal phase-based framework. Inertia and Newton's laws. In uniform motion, a system carries its internal phase structure with it. With no external phase gradients imposed, no acceleration occurs. This yields Newton's first law. An object in motion remains in motion unless acted upon by an external interaction. Inertia arises as resistance to changes in phase structure. Applying a force requires reconfiguring internal phase relationships, which manifests as resistance proportional to mass. Newton's second law follows directly. force equals mass times acceleration. Acceleration is the response to an imposed phase gradient. Mach's principle and the role of the universe. In quantum atom theory, phase gradients are meaningful only relative to a larger environment. Local inertia and gravity are defined with respect to the collective phase background of the universe. This naturally incorporates Mach's principle. The distribution of mass energy in the universe determines local inertial frames. The inverse square geometry links every object, however weakly, to the rest of the cosmos. Dirac's large numbers and cosmological scaling. Dirac observed striking numerical relationships between atomic and cosmological constants. Quantum atom theory interprets these not as coincidences, but as consequences of a single universal phase process operating across scales. Local phase delays at the atomic scale and global phase structure at the cosmological scale are expressions of the same geometry. The universe may be understood as a sphere of probability, with local interactions nested within a global phase framework. Entropy, probability, and the arrow of time phase exchange is inherently statistical. Each interaction disperses phase information into a larger number of degrees of freedom, increasing entropy. The arrow of time emerges from this irreversibility. While microscopic laws are time-symmetric, macroscopic phase accumulation is not. Least time and least action light follows paths of least time, because these paths minimize total phase delay. Matter follows paths of least action for the same reason. Both principles arise from the same requirement. Phase propagates spherically, and interactions occur where accumulated phase delay is extremal. Paths emerge statistically from these interaction points. Relation to relativity. Einstein's relativity describes how clocks and rulers behave in gravitational fields. Quantum atom theory provides a microscopic explanation. Time dilation occurs because phase exchange is slowed by interaction density. Light bends near massive objects because phase surfaces tilt, not because photons experience force. Curved spacetime is an effective description of underlying phase geometry. Antimatter and causal closure. In quantum atom theory, antimatter annihilation represents the closure of a phase history. These events release energy completely, leaving no residual structure to seed future phase accumulation. Matter supports forward phase continuation. Annihilation completes causal loops. This preserves known physics while offering insight into time asymmetry. Conclusion. Quantum atom theory presents a unified conceptual framework in which time, gravity, inertia, and causality emerge from irreversible phase exchange governed by spherical geometry. The universe, in this view, is not constructed from particles moving through spacetime, but from phase relationships unfolding probabilistically, one interaction at a time. This work is offered as a conceptual foundation and a guide for further discussion, visualization, and exploration.